Welcome to the video on chemical composition. This is Chapter 6 of our Introductory Chemistry series, presented by Dr. Sylvia Esbjornsen. In this video, we will explore key topics including counting atoms and molecules by weight, using chemical formulas as conversion factors, and calculating both percent composition and empirical formulas. Our learning objectives for this video are to master various conversions between atoms, moles, and grams, and to learn how to determine chemical formulas from experimental data. Consider the dietary mineral sodium. We consume it primarily as sodium chloride, or table salt. Understanding the relationship between sodium and the total amount of salt is important, as excessive sodium intake can affect blood pressure. The FDA recommends limiting daily sodium intake. However, because sodium chloride consists of different elements with different masses, we cannot tell the amount of sodium just by looking at the formula, sodium chloride. We need calculations to determine the amount of a specific element in a compound. By using chemical formulas alongside atomic and formula masses, we can accurately determine the amount of a constituent element, such as finding how much iron is in iron ore, or chlorine in a chlorofluorocarbon. Think about how hardware stores sell nails by weight. Weighing them is much more efficient than counting each one. Chemistry uses a similar principle to count atoms in a given mass of an element. For instance, if you know the weight of a dozen nails, you can calculate the total number of nails in a bulk purchase. This is a simple application of dimensional analysis. Here we see the conversion factors applied. First, the weight per dozen nails, and second, the number of nails in a single dozen. These factors allow us to bridge the gap between mass and count. Atoms are far too small and numerous to count individually. Even counting non-stop for a lifetime would not be enough to count all the atoms in just a single grain of sand. We must use mass as a proxy for counting. Just as a dozen is a convenient unit for nails, chemists use the mole to count atoms. A mole represents a specific, very large number of particles. This value is Avogadro's number, named after Amedeo Avogadro. 1 mole of any substance, whether it be marbles or sand grains, contains 6.022 times 10 to the 23rd power of those units. While a mole is a massive number of particles, it often corresponds to a reasonable, observable amount of material, such as the copper in a handful of pennies or the gas inside balloons. The size of a mole is defined as the number of atoms in exactly 12 grams of carbon-12. This precise definition links mass to the number of atoms, enabling chemists to count atoms by weighing them. To convert moles of helium to the number of atoms, we use Avogadro's number as a conversion factor. As shown here, 3.5 moles of helium results in approximately 2.1 times 10 to the 24th power of helium atoms. Now let's look at converting the number of silver atoms to moles of silver. We start with 1.1 times 10 to the 22nd power silver atoms, and use the reciprocal of Avogadro's number as our conversion factor to find the total moles. This slide demonstrates that while 1 dozen large nails and 1 dozen small nails share the same count, their weights differ significantly. This is analogous to how different elements have different molar masses. Similarly, 1 mole of sulfur atoms weighs 32.06 grams, while 1 mole of carbon atoms weighs 12.01 grams. The number of atoms is identical, but the total mass depends on the individual mass of each atom. Molar mass is linked to atomic mass. The atomic mass unit, or AMU, is 1/12 the mass of a carbon-12 atom. The molar mass of an element is numerically equal to its atomic mass expressed in grams per mole. For instance, 1 copper atom has an atomic mass of 63.55 atomic mass units, meaning 1 mole of copper atoms has a mass of 63.55 grams. Thus, the molar mass of copper is 63.55 grams per mole. The mass of 1 mole varies by element because atoms differ in their individual masses. Lighter atoms result in a smaller mass for 1 mole, while heavier atoms result in a larger mass. To convert from grams to moles, we use the molar mass as a conversion factor. For a 0.58 gram diamond, we use the molar mass of carbon, 12.01 grams per mole, to calculate the moles present. When we need to go from grams to atoms, we use a 2-step process. First, convert grams to moles using the molar mass, and then convert moles to the number of atoms using Avogadro's number. For example, to find the number of aluminum atoms in 16.2 grams of aluminum, we divide the mass by its molar mass to get moles, then multiply by Avogadro's number to find the count of atoms. We can also count molecules by the gram. For elements, molar mass is per mole of atoms. For compounds, it is the mass of 1 mole of molecules or formula units. To perform these calculations for compounds, we first determine the formula mass, which is the sum of the atomic masses of all atoms in the chemical formula. Let's calculate the mass of 1.75 moles of water. We determine the molar mass of water by adding the atomic masses of 2 hydrogen atoms and 1 oxygen atom. With a molar mass of 18.02 grams per mole for water, we multiply this by 1.75 moles to find the total mass of the sample. To find the mass of a large number of molecules, such as 4.78 times 10 to the 24th power of NO2 molecules, we first convert molecules to moles, then moles to grams using the molar mass. Chemical formulas also act as conversion factors. Just as we use the ratio of leaves to clover to count items, we use the subscripts in a chemical formula to relate atoms to the molecule. The chemical formula for a compound provides a direct conversion factor between moles of the compound and moles of its constituent elements. For instance, in carbon dioxide, the formula CO2 tells us 2 moles of oxygen atoms for every 1 mole of the entire molecule. This relationship holds true regardless of the units used, as long as they are consistent. Whether we are dealing with individual molecules or moles of a substance, the ratios defined by the chemical formula subscripts remain the same. Let's apply this to a concrete example. Calculating the moles of oxygen in 1.7 moles of calcium carbonate. Using the formula, we know there are 3 moles of oxygen for every 1 mole of the compound. When we need to find the mass of a specific element within a given mass of a compound, we extend this logic. For example, to find the mass of sodium in 15 grams of sodium chloride, we use the stoichiometry of the compound alongside molar masses. Essentially, the chemical formula provides the bridge between the macroscopic world of grams and the microscopic world of moles, allowing us to quantify the composition of complex substances. Beyond molar relationships, we often describe compounds by their mass percent composition. This value represents an element's percentage of the total mass of the compound. To find the mass percent of an element, you divide the mass of the element by the total mass of the sample. Here, we see an example where a sample of chromium reacts with oxygen, and we can calculate the percentage of chromium in the resulting oxide. Mass percent can also be used as a conversion factor between the grams of a constituent element and the grams of the total compound. It is a very practical way to understand the purity or composition of a substance. For instance, if sodium chloride is 39% sodium by mass, this tells us there are 39 grams of sodium for every 100 grams of the salt. This ratio is a powerful tool for stoichiometric calculation. Let's put this into practice with a health-related question. If the FDA recommends consuming less than 2.4 grams of sodium per day, how much sodium chloride can an adult safely consume, knowing it is 39% sodium by mass? We can also derive mass percent composition directly from a chemical formula by comparing the mass of a specific element in 1 mole of the compound to the compound's total molar mass. This is shown here for chlorine in FREON 114. This calculation requires identifying the total moles of an element present in 1 mole of the compound and then performing the division based on molar masses. Continuing with the example of Freon 114, we calculate the contribution of the chlorine atoms to the total molar mass of the compound to arrive at the final percentage. Understanding these principles is vital in health contexts, such as the fluoridation of public drinking water. Fluoride is essential for dental health, but balance is key, as excessive intake can cause issues like dental fluorosis. In practice, water is often treated with sodium fluoride. Chemists use the mass percent composition we've discussed to calculate exactly how much sodium fluoride is needed to achieve the target fluoride level in a large water supply.